Question 6 says a capillary tube of radius r contains a liquid density 1 gram per centimeter cube. Surface tension S is 0.01 Newton per meter up to the height 12 centimeter as shown. If R, 2R are the radius of curvature of liquid surfaces at top and bottom respectively, and theta, theta naught are angle of contact at top and bottom respectively, then, well, obviously the question is from the topic surface tension, and it's given that the radius at the top surface, radius of curvature of liquid surface at top is R, and the capillary tube also has radius R, which means that the center of curvature is like this, and this is the situation at the top surface, because the radius of meniscus is same as radius of the tube, which actually means that the angle of contact at the upper surface is 0. Okay, so the angle of contact at the upper surface has been called theta, which actually means theta is 0. This is at R, and so theta is 0 degree is the correct option, and the other one is at distance of 12 centimeter. Let's say this is 12 centimeter, and at the lower surface radius of meniscus is 2r. So that means if here is the center of curvature, let's say here is the center of curvature, the surface is forming like this. The center of curvature is here, and this distance is 2r. This will then r, and this is the angle of contact theta naught. So this is also the angle of contact theta naught. Cos theta naught is 1 by 2, r by 2r. So we have cos theta naught equal to 1 by 2, which gives us that theta naught is 60 degree. So that means option A is also correct. And now we have to evaluate the value of R2. So for doing that, we can just look at the variation of pressure. So if pressure here is say P naught, then at this point pressure is P naught minus 2s by the radius of meniscus there, R, and then the pressure increases by rho gh, h is 12 centimeter, let's say it's rho gh, and then it is further decreasing by 2s by the radius of meniscus here is 2r, and then we come to the atmospheric pressure again. So simplifying this, we get the expression rho gh is equal to 2s by r plus s by r, or 3s by r, and that gives us that r is equal to 3s by rho gh, right? Let's put the values now. 3s, so it's 3. Let's say s is 0.01, that means 10 to the power minus 2 SI units, and rho is 1 gram per cubic centimeter. In SI it will be 1000 kg per cubic meter. G is 10, so these two together is 10 to the power 4. H is 12 centimeter, so it's 12 into 10 power minus 2. So we can put 10 to the power 2 in the numerator. This is the value of R in meter. Okay, R is coming out to be equal to 1 by 4 into 10 to the power 4 meter. Now to get this value in millimeter, we need to multiply it by 1000. If we do that, we find that R is simply 1 by 40 millimeter. And if we look at the options, B is matching. So B is also correct and D is incorrect. That means for question 6, A, B and C are the correct options. Let's go to the next question now. Question 7 says, a uniform thin hemisphere is in equilibrium over an inclined plane having inclination theta equal to 30 degree as shown. Alpha is the angle made by flat circular plane of hemisphere with inclined plane. If vector tau 1, tau 2 are the torques of frictional force and normal reaction about the center of mass of the hemisphere, then there are the options given. Option A says alpha is pi by 3, option B says alpha is pi by 6, option C says vector tau 1 plus tau 2 is 0, and option D says vector tau 1 is equal to vector tau 2. Well, the body is in equilibrium. It has both translational equilibrium as well as rotational equilibrium, which means net torque about any point is 0. So if we consider the center of mass, we know that for a thin hemispherical shell, which is what this body is, the center of mass is somewhere here at distance r by 2 from the center of curvature of the hemisphere. So this is r by 2. Now if I consider torque of mg about center of mass will be 0, because we can consider that the line of action of mg is passing through C, and since net torque is 0 about any point including about point C, so torque of frictional force plus torque of normal reaction, but torque of mg is 0 anyway, so that means this is equal to 0 for rotational equilibrium. So that means option C is correct and option D is not correct, right? Their magnitudes will be equal, but their directions have to be opposite. So D is not correct. Let's now evaluate the angle alpha. Okay. Now for evaluating angle alpha, let's redraw the figure. Let's say this is the hemisphere, something like this. And this is the base. This is the center of curvature. This is the center of mass, C. And for equilibrium, one thing is for sure. The vertical line through C, the line of mg, must pass through the point of contact. So this is the point of contact. We can give it a name. Let's call it A. And this is the center of curvature. Now this distance we know is r by 2. And if we join this angle will be 90 degree, because this is tangent and this is radius, so this is 90 degree angle and this length is r. Further, this angle is given as 30 degree. So this angle also is 30 degree because this line is perpendicular to the incline and this line is a vertical line perpendicular to the horizontal. So this angle is 30 degree. So now we have a triangle OCA, in that one side is r, the other side is r by 2 and one angle is 30 degree, and this angle also is going to be alpha, which is what we have to find, because alpha is the angle between the incline and outline of the base of the hemispherical shell, and that angle is alpha. Now if we apply the sine rule in this triangle, what do we get? We get r by 2 by sine 30 degree equals r by sine of this angle, and sine of this angle will be same as sine of 30 degree plus alpha. Okay, so that means this is equal to sine 30 degree plus alpha. Now solving this we get 30 degree plus alpha. In fact, sine 30 degree plus alpha is 1, and that means 30 degree plus alpha will be 90 degree, which gives us alpha at 60 degree, which is actually equal to pi by 3. So that means option A is also correct for question 7. Let's go to the next question now. Question 8 says, if U1 and U2 denote gravitational potential energy of uniform thin hemispherical shell of mass m and spherical shell mass 2m respectively, then let's use result for self gravitational potential energy of a uniform thin spherical shell. So if we have a shell like this, and if its mass is m and radius is r, we know that u is minus gm square by 2r. We shall use this result. Now if we look at the expression for u2, u2 is the self potential energy, gravitational potential energy of a thin spherical shell of mass 2m and radius, let's say, is r. In that case, the expression for U2 will be minus G 2m square by 2r, or simply minus 2gm square by r. So that means option A is clearly correct. Now we have to consider gravitational potential energy of a thin hemispherical shell, and which is being called U1. Now we can see that when we are a complete shell is made up of two hemispherical shells, each of mass m, and if energy, self energy of each one is U1, then the total energy should be equal to U2. So that means we can say U2 is self energy of 1, which is say U1, plus self energy of 2, which is again U1. So that means 2U1 plus gravitational potential energy of interaction between, let's say, part 1 and part 2. Okay. Now each term is going to be negative. So it's very clear now, from this it's very clear. The magnitude of each term is positive, but each term by itself is negative. So it's very clear now that 2 times of magnitude of U1 is less than magnitude of U2. And which means options B and D are incorrect. Option C is correct. Let's go to the next question now. Question 9 says, a water tanker kept at rest having water and a pipe at its bottom. Initially, nozzle of pipe is closed. As we open the nozzle of pipe, then tanker, option A says tanker will not move at all. Option B says tanker will start moving to right. Option C says tanker will start moving to left. And option D says emerging liquid has horizontal component of velocity. Obviously, we can apply the conservation of linear momentum for the system, and we can see that there is no external horizontal force on the system. So that means its linear momentum is going to be conserved horizontally, right? Now what will happen, as this nozzle is opened, the liquid will rush from right to left to come out of this, because as per the geometry given, we can see that the liquid is going to rush from right to left. And if that is the case, that means the moving liquid has momentum towards left, which will impart momentum to the tanker towards right, so that horizontal momentum remains 0. So that means the tanker will start moving towards right, and as the liquid is coming out, so the horizontal component of the liquid which is coming out is same as the horizontal component of the tanker. So that means the emerging liquid has horizontal component of velocity. That will also be true. Okay. So if considering all this, we see that option B is correct, and option D is also correct. Options A and C will not be correct. So that means for question 9, by simply conserving linear momentum horizontally, we get the answer, and options B and D are found to be correct. Let's go to the next question now. Question 10 says, in the shown arrangement of 2 blocks and 2 light strings 1 and 2, if delta L1 and delta L2 are the elongations in string 1 and 2 respectively, then this is the arrangement shown. The blocks have masses 2m each. String 1, Young's modulus is 2y, area of cross section is A, length is L. And for string 2, Young's modulus is y, area of cross section is A, and length is L. Option A says delta L1 is this. Option B says, well, all the options are about delta L1 and delta L2. So let's find the values of the elongation. Obviously, the question is from the topic elasticity. So elongation, the expression is the tension T, if it is uniform, tension T by area of cross section into Young's modulus and in the numerator is original length. So this is the formula we can use. First of all, for the string 1, tension in the lower string, let's call it T1, is simply 2 mg. Okay, whereas the tension in the upper string is going to be 4 mg. So delta L1 will be then 2 mg into the length, which is L, divided by area of cross section, which is A, and Young's modulus is 2y. This simplifies to mgl divided by ay. Okay, so that is delta L1. Well, what we have got does not match with option A. Let's evaluate delta L2 also, and delta L2 will be then tension in the string 2 is 4 mg, so it's 4 mg into length L divided by Young's modulus y into area of cross section A, and we can see that delta L2 is matching with option C. Option A is incorrect, and delta L2 we can see that is equal to 4 times delta L1. So delta L1 is delta L2 by 4 is also correct. That means option D is also correct, and options A and B are incorrect. Let's go to the next question now.